Hello, this is Ryan Linfield, and I'm going to give you a crash course on crashing. This is my quick and dirty explanation of what a buffer overflow is. So first things first, starting off, talking about buffer overflows or crashing applications. First thing that we need to understand is the concept of your CPU or central processing unit. We know that every computer, laptop, tablet, smartphone has a CPU. The CPU handles instructions, and one of the ways that it does this is by looking at particular registers. So a register is something that the CPU uses that points to different memory addresses. There's lots of different registers. The quantity of registers depends on the type of processor that you have. ARM is different from SPARC, is different from Intel or x86, but what we're going to focus on today is x86 exploitation. The three registers that I'm going to teach you about today, the three most important ones for our purposes, are going to be the base pointer, or EBP, the stack pointer, or ESP, and the instruction pointer, which is EIP. There's more pointers than this, but these are the ones that we actually care about for the moment. So our CPU has these registers. What is a register? Just a little tiny chunk of memory that effectively holds a memory address. So when we're processing an application, we can look at where the stack begins and ends. So next layer of this is, well, what the heck is the stack? The stack is effectively a chunk of memory that we've laid out for a program. So you know when you look at your laptop, for instance, I'm on a MacBook Pro here. I think it's got 16 gigs of RAM. Of that 16 gigs, let's just lay that out as this huge space that can be utilized for one thing or another. Whenever I want to run a program and that program gets laid into memory, it gets done by defining a stack. A stack is just a chunk of memory. So this big square here that you see on the outside, that represents, and I'll just put it up here at the text tool, 16 gigs of RAM. Now, my program actually only needs about 100 megs. So I realize that this isn't really to scale, but when you allocate that memory, you start off with what's called your base pointer, or EBP, which is effectively just a memory address. And this is the base of the stack. So from previous discussions, reading, understanding, just knowing the prerequisites of the conversation, you should know that the stack is a structured chunk of memory that's being utilized by an application. The EBP, or base, is where the stack begins. Now, throughout the life cycle of this application, the quantity of memory that it takes up is going to change. Just imagine that you're using your browser of choice. You open a new tab, you load a new web page, you log in, there's additional cookies, there's resources. Well, as you're doing this, the quantity of memory being utilized is going to grow. If I was to close a tab, well, that's going to free up some memory, so the quantity of memory is going to shrink. Where we actually sit in memory as the stack grows and shrinks is defined by our stack pointer, or ESP. The ESP points to this top of the stack, which is how much memory are we currently utilizing. So the ESP changes, your base pointer does not change. This is a fixed address that is defined at the beginning of execution, and we basically calculate how much memory we're using by how far are we from that base. Now, within this stack, there's a lot that's happening. There's, DLLs and things that are used by programs that are going to be loaded into memory. One of the interesting things for our discussion is a buffer. And a buffer, like the name suggests, is just kind of a chunk of memory here that's been allocated by the developer. And this is going to store user-supplied data. So, for instance, what we're going to look at today is a web server, a very simple web server. And we know that web servers effectively, let me just draw a little box down here for a web server. Web servers listen on what port? Anybody remember? Should be the least of our worries at this type of discussion. But TCP port 80. And the way that a web server works is it listens for incoming requests. And when a user makes a request, like give me index.html please, that GET request that's being sent by the user is being placed into a buffer. And the program looks at that buffer and it goes, oh, they want index.html. He looks to the file system and he does an HTTP response that contains that. So the way that buffer overflows occur is that when a user supplies some input, if we don't do sanity checking, and that is this input valid? Is this a realistic request? is this user doing something that makes sense? If we check or sanitize that, we could prevent buffer overflows. But if we're not using any type of input validation, you're saying, hey, whatever the user requests, just place into this buffer and then go ahead and, handle it, execute it. So a lot of times when we want to do fuzzing or seeing if an application can be broken, you'll make a ridiculous GET request. In my example, I'm going to put 2,220 because that's just the number that I thought of. 2,220 capital A's into a buffer. So I'm going to request just this obnoxiously large file name. Imagine a file name that was just all capital A's and it was 2,000 characters in length. If that's larger than the space that the programmer has allocated to this buffer, then what we're going to get is a buffer overflow. So coming back to my diagram on the right here, we're basically going to shove in so much data that it's going to overflow this defined area where things are supposed to be stored, and it's going to corrupt other parts of the application here. Now, this isn't going to get me a remote shell. This isn't going to get me, the user database. Not yet, because we're not looking at exploitation yet, just simply the buffer overflow. What I'm going to do is make a massive request to a web server, and if they don't do any type of input validation, and that is saying, the maximum request can only be 400 characters in length or 200 characters in length. If there's no bounds checking, I'm going to be able to force this huge request in. It's going to be placed into memory, and it's going to overwrite other parts of the application that are actually necessary and cause the application to crash. So this can actually be demonstrated really easily with OllieDebug. So here's my Windows host. This is just a virtual machine. Here we see the IP address. That's going to be necessary for hitting the actual web application. I'm going to kick off OllieDebug, which is the process equivalent of Wireshark. I'm going to go ahead and open my mini share application. This is a web server, a very simple web server. And what we see here, it's really pretty neat. On the left side, this is the actual program in assembly code. To the right, these are the registers that we talk about that the CPU uses. So here's my base pointer, here's my stack pointer, here's my instruction pointer. You've got your EAX, EBX, ECX. These are actually used for like addition, subtraction operations. We'll talk more about the registers in another session. I'll make a separate video for that. But effectively, when I hit play here, it's going to run the application. We see down there that the state changed to running, and we see that the application here is actually launched. So mini-share is up and running. If I wanted to share an actual HTTP document, like I'll just throw this report in there. So now this report is being shared on my web server if somebody was just to go to report.html. So I'm going to come over here and ask for /report.html, and there it is. It's just a report that I had written or generated from a scanning utility. Now, just to refresh, there's my report.html. There's only one file being shared. And just to clarify, this window that you're looking at is Firefox running within Mac OS X. This over here is my Windows XP host. So next, I'm just going to bring up a terminal session. And my working directory is just, I've got a mini share folder here, which has got my exploit. I'm going to cat just to show you what the script looks like. This is a simple Python script that's going to basically create a TCP socket to the destination IP of 172.16.123.133. It's going to connect on port 80, which you'd expect for a web server. And what it's actually going to do is do a GET request. And that GET request is what a browser, whether it's Internet Explorer, Chrome, Firefox, whatever you're using, that's how it talks to the web server and actually makes a request. He's saying, hey, web server, I would like to get, and then we define the resource. Well, my resource is x41. Well, x is also 0x, which is hex, and 41 is the hexadecimal representation of a capital A. So I'm going to do a capital A times 2,220. That's just the number that I picked. So I'm requesting a resource that's effectively, the name of it is just 2,000 capital A's. And if they're not doing any type of boundary checking, all that's going to get shoved into the buffer. The buffer is going to overfill, and that's going to overwrite other important parts of the application and cause it to crash. So let's quickly just run this script and it returns. So it doesn't really tell me much, except we know that it was able to connect and go ahead and send that request across. If I move back over to VMware Fusion, we look here, and let's take a look. It's locked up pretty well. Yep, it's angry. Looking at Ollie debug, we can see here that our stack pointer it contains this ASCII of A. Down here, our instruction pointer, all 41s, and when we take a look at what memory actually looks like, there it goes. It's all 41s, where previously it actually had instructions there. There was, what the program was supposed to be doing. But because there was no boundary checking, we shoved in all those A's, we broke the application. Now this is just the tip of the iceberg. We crashed an application. This is effectively denial of service. The app is locked up. We didn't get a shell, we didn't do anything yet, but if we can shove all these A's into memory, I can shove another program into memory. It might be calc, it might just simply be a calculator, or it might be something really slick like a shell or an agent that I can use to remotely control this device. And what's really neat is it's going to be sitting in memory, and it's not going to be on the disk. Whenever we push things into memory, if they're not watching what's happening in memory, we can a lot of times bypass things like intrusion detection or firewalls because we're running under the permissions of another process, that process being our web server. So that was just a quick and dirty explanation on how to crash an actual service. And you see here the amount of code that it required was minimal. I just created a TCP socket. I did this really ugly request, and because that application didn't do any boundary checking, I shoved those 2,000 A's into this little tiny buffer, which effectively corrupted memory and caused the application to break. In a future session, I'm going to show you how to take your own code, shove your code to memory, and get that computer to do what we want it to do. Thanks for watching.